to here, okay, to this picture. Let me just talk. So this is so what is shown here is that this is the full electron spectrum of water molecule. Okay, so this is what we will see using if you like using a low energy photon, so-called helium-1 photon, which is 21.2 electron volt. Okay, so but I don't want to talk about this. This is what you measure and what you see if you do full electron spectroscopy, right? So you can see this kind of tour at the glow side. You can see this in Professor Westwood's lab. He has done a lot of these helium-1 full electron spectroscopy in his past, and for the Waterloo student, you can come down to my lab and I can show you some of this equipment. But what is happening here? How do you generate this peaks and so forth? So it's easier to understand if you have show this picture. Let me look at this picture instead. This picture is an MO diagram, molecular orbital diagram, showing the molecular orbital of water molecule. So you can see that so 1A1 state. Okay, so this A1, B1, and B2, so forth. They are molecular orbital destinations. So they are kind of like the equivalent of S orbital and P orbital and so forth. But of course, they have molecular structure associated with this, and they have symmetry along with this. Okay, so I don't want to explain this molecular orbital notation, but it suffices to say that they are a way to designate the symmetry of the orbital that you see. So for example, A1 here, A is molecular symmetry, means totally symmetric A1, and it corresponds to the oxygen 1s electron localized in there, right? So this is a totally no connection to your proton, right, to the hydrogen atom, because it's just a 1s core electron sitting deep down in the core. So there's no bonding involved. So this is 1s 1A1 orbital. You can see it's very deep because the binding energy or the orbital energy, right, is about 558 electron, also way deep into the bond. And then you go a little bit higher. You have 2A1 orbital, which correspond to the oxygen 2s orbital, and still very deep, so-called very deep into the core. And then as you go further up, you now have binding effect, right? So you now have a 2p, oxygen 2p, binding with the hydrogen 1s electron in either symmetric or anti-symmetric way. So here you have, for example, this orbital corresponds to, oxygen in the middle, and then you have an s orbital which is spherical like this, right? So you have plus or minus, right? Your p orbital has a sign, and the s orbital is, of course, all plus. So you have this kind of effect. You have a Lodo effect like this. So that's a 1b2 orbital. So it has to do with symmetry, and then the next one up is 3a1, and the last one, of course, is the long. So one is this orbital has to do with the p orbital in this way. The second orbital has to do with the p orbital lying this way, right? You remember? And finally, the last p orbital is the one out of the plane of the paper, and is drawn in a tilted way so you can see. So you can see that, you can tell, of course, the last orbital, the highest lying orbital, the HOMO, so-called highest occupied molecular orbital, is the lone pair orbitals, right? So they are not binding to the hydrogen atom like this. Okay. So each of these, so this is a molecular orbital diagram, right? And each of these correspond to a certain energy that we see. deep into the electronic structure, right? So I'm taking a little bit time to discuss this because later on when we talk about electronic structure, we will need some of these concepts. So I'd like you to appreciate this connection to first molecular electronic structure and then band structure, which has to do with the electronic structure of the solid itself as we go through. Okay, so this is one way to think about this. This is basically so-called single electron picture. You are treating, chemists in particular is very big on this. The chemists like to think of these electrons in their orbitals. So these are molecular orbital theory. And of course, in real life, that's not true. You cannot really divide these things into little well-defined package of orbital that electron move about. So really, you should talk about the entire wave function. You should not divide them up into a little package of one electron each kind of thing, right? But chemists have been doing this for years, and it's a useful concept to do simply because it's a nice way to understand how the injection of the electron occurs. Now, if you want to do a little bit better than this one electron picture, you can do it in a configuration, so-called molecular configuration. Now, it's written like this, right? So you can write it as, okay, well, for the neutral molecule, you have all this electronic configuration. I'm not sure you can see. Let me try to blow this up a little bit. So you can see this electronic configuration, you know. It's just like in atom, you talk about carbon is 1s2, 2s2, 2p2 kind of thing like this. So this is how you build your periodic table. In molecule, you do the same. You have this MO molecular orbital, and you put electron in there. So 1A, 1, 2 represent 1A1 electron in this orbital, 1A1, you know, and so forth. And then you sort of build it up, just like your atomic electronic configuration. Then what you could do is that you can say that, well, if you remove one of the highest occupied electron, what would happen if I remove this one, right? Let's say the 1B1 orbital, I take one of these out, right? Then what do I end up with? I have all the previous molecular orbital the same, except I have one less 1B1 orbital. So you can see in the neutral molecule, I have 1B1, 2, right? In the first one here, I just have 1B1, 1, right? To this little exponent indicate the number of electrons in that orbital. So that corresponds to the grounds, what the people call ground ionic state, because this is an ion state. Because why? Because, well, you have one less electron in there. So you have neutral molecule. You have removed one electron from the 1B1 orbital, and you got this ground, so-called ground ionic state, H2O+. And then, of course, you can do the same. You can say that, well, I don't want to remove this from the 1B1 orbital. I can remove it from the second line orbital. I can remove from this one, the 3A1 orbital, instead of the 1B1 orbital. And you get a state that is a little bit higher in energy, because you need more energy to remove this 3A1 orbital, right? So now you would have this one here. You would have 1B2, 2, 3A1, 1, right? There's one missing from this, right? You need 2 electrons to fill the MO orbital, and then you leave 1B1, 2, right? So that's a removal of the second orbital from there. So that is called a total wave function, right? So the reason why you write it this way is to make sure that people understand that you're really talking about an entire package of electrons. This single molecular orbital approach is good in terms of trying to understand what happened, but in real life, you really should talk about the entire wave So this is a good way, right? The molecular configuration, the electronic configuration is a good way of saying this. So the one that you see, 1B1 correspond to the so-called X state, right? So the chemical physicists are not very imaginative people. They just call the ground